నేను నేను మాట్లాడేది వినిపిస్తుందా మీకు? చూడండి.
Ladies and gentlemen, a very good morning to one and all. I, Daniel Salas Kumar, Assistant Professor from the Department of Mechanical Engineering and Coordinator for this FDP, take privilege of hosting this event. It gives me immense pleasure to extend you a very warm welcome on behalf of the Department of Mechanical Engineering, Lendi Institute of Engineering and Technology, to this Series 2 of 1 week online international FDP on trends and challenges in the development of electric and hybrid electric vehicles. I hope you have learned much in the previous series, and I believe that you would have an even better experience for this FDP too. We have got a large number of responses from a very diverse group who have joined us both from India as well as abroad. We thank you for showing interest to be a part of this FDP. This morning, I would like to acknowledge the online presence of our dignitaries for the day. Our professor and convener for the FDP, Dr. K. Sridhar sir, our chief guest for the day, and keynote speaker for the day, Mr. T. Rohit from TE Company, Germany, and our session speaker for the day, Dr. Krishna Kumar Gupta sir from Top Institute of Engineering and Technology, Patiala, and all the others present here. To begin with, I would like to invite our convener for the FDP, Dr. Sridhar sir, to give his opening remarks, and also request him to give a brief introduction of this FDP and address the gathering. Over to you, sir.
Good morning to all the dignitaries and welcome to the participants. For today's session, most of the automobile companies are going to switch to electric, a cleaner and sustainable alternative. An electric revolution comes to the automobile sector in India, but the industry is facing a shortage of talented and skilled engineers needed to transition to electric drives as a primary source of motive power to conduct this course. The program focus on provide theoretical as well as practical aspects of EV infrastructure development to the participants and thereby enable them to promote industry and institute collaborations by working on current research problems. Related to it, the department has organized Series 1 between 26th October to 30th October 2022. We have received immense response from the research scholars, industrial executives, teaching faculty during the Series 1. To cover some more concepts, the Series 2 is planned. This FDP will provide an excellent opportunity to faculty members and research scholars to have an interaction with nationality and internationally renowned experts in the area of electric vehicles. We have received good registrations, more than 1,500 registrations across the globe from different countries. And in India, all states, including Northeast and Union Territories. In today's section, Mr. Rohit from T Connectivity, Germany, will deliver his keynote address. Mr. Rohit did his bachelor degree in mechanical engineering from Jawaharlal Nehru Technological University, India. and masters from Germany. And he has good experience with the product development related to product design and development in Airbus Group, Hamburg, a leading manufacturing unit for domestic and defense Airbuses. And Mr. Rohit presently with TE Connectivity, Belgium, Germany, as a product manager e-mobility. He is monitoring project status leading to entire project team in completing all project phases, including conception, design, validation, and initialization. And he is setting project timeliness and milestones according to customer requirements. Now I am welcoming Mr. Rohit to deliver his keynote address. Welcome, Mr. Rohit.
Hello all, can you guys hear me?
Yes, sir, you're on.
Yes, we are audible.
Thank you.
Audible,
Thank you.
Mr. Rohit,
Thank
sir.
you.
Please start your section. Please deliver your
Thank
keynote
you, Sridhar
address.
sir. Thank you, Sridhar sir. Sorry for this inconvenience. I was in mute. Okay. Good morning, everyone. I'm Rohit Tariboina, and I'm working in TE Connectivity Germany as a project manager for e-mobility department. On behalf of TE Connectivity Germany, I'm delighted to join you guys on the one-week international online faculty development program on the trends and challenges in the development of electric and hybrid electric vehicles as a series 2, organized by the Department of Mechanical Engineering of the Lendi Institute of Engineering and Technology. First of all, I would like to thank the management of Lendi Institute of Engineering and Technology for giving me this opportunity to speak at this conference on e-mobility. I would also like to convey my regards to Sridhar sir for this opportunity. I am so excited to share my insights with you, and I hope that we can all learn from each other's experiences. I strongly believe this faculty development program is an excellent opportunity for faculty members, researchers, scholars, and the students to gain theoretical as well as a practical aspects of electric vehicle infrastructures and developments. Today's event is especially significant after a tough 2020 that made the world rethink how we do the development, namely how to drive the growth with sustaining our society and planet. My goal today is to help you to understand the scope of electric vehicles and the need to electric vehicles in India and discuss the current challenges and finally how to overcome these challenges. As you all aware, India is one of the most populated countries in the world with a population of over 1 billion people. India has enormous potential to produce these electric vehicles and use them as a means of mode of transportation. In fact, it is predicted that by 2030, one third of all the cars on the road will be hybrid or electric. The push of electric vehicles is driven by the global climate agenda, which was established under the Paris Agreement to reduce the carbon emissions in order to limit the global warming. The global electric mobility revolution is today defined by the rapid growth in electric vehicle uptake. About 2 in every 100 cars sold today are powered by electric vehicles, sales for over 2020 reaching over 2.1 million. The global electric vehicle fleet totaled around 8 million in 2020, with electric vehicles accounting for 1% of the global vehicle stock and 2.6% of the global car sales. Falling battery costs and rising performance efficiencies are also fueling the demand for electric vehicles globally. India is currently in need of this transportation revolution. The current trajectory of adding more cars running on expensive imported fuel and cluttering up the already overcrowded cities suffering from the infrastructure bottlenecks and intense air pollution is no longer feasible. The transition to electric mobility is a promising global strategy for decarbonizing the transportation sector. India is among the handful of countries that support the global EV30 at the rate 30 campaign, which aims for at least 30% of new vehicle sales by the year of 2030 to be electric. The government of India has taken various measures to develop and promote EV ecosystem in country. The FAME scheme, more or less called as the Faster Adoption and Manufacture of Electric Vehicle scheme, the PLI scheme for automotive component manufacture, the ACC schemes for the supplier sides. These are the basic examples that we could understand the way how EV is promoted by the Indian government. Despite of all these strategic growths and the promotions by the government, we still have some challenges for the Indian EV manufacturers to overcome. Mainly the battery manufacturing. It is estimated that by 2020 and 2030, India's cumulative demand for batteries would be approximately around 900 to 1100 gigawatt hours of requirement. However, there is a concern over the absence of manufacturing base for batteries in India, leading to sole dependence on imports to meet the rising in demand. As per government data, India imported more than $1 billion worth of lithium ion cells in 2021, even though there is a negligible penetration of electric vehicles and battery storage in power sector. The second challenge, lack of charging stations. In 2019, India was reported to have only 650 charge starting stations, which is quite less in comparison to our neighborhood counterparts, who already have over 5 million charging stations. Example, China. Lack of charging stations makes it unusable for the consumers in covering the long ranges. Moreover, it takes up to 12 hours of full charge to charge your complete vehicle in your own home using a private light duty slow charger. Also, the cost of a basic electric charge is much higher than the average price of a car running on a conventional fuel. The third challenge, the policy challenges. EV production is a capital intensive sector requiring long-term planning to break even and profit realization. Uncertainty in government policies are also causing more concern to the investors to think a lot in order to have any kind of an investment to be developed on the EV sector. This is also one of the concern where you see because of this there is less number of people who are willing to go into investment in the EV sector from a private point of view. Fourth challenge, lack of technology and skilled labor. India is still technically deficient in the production of electrons that form the backbone of the EV industry, such as batteries and semiconductor controllers. EV have the high service costs, which require high level of skills, but India lacks the dedicated training courses for such skill development. And the last challenge would be the unavailable of materials for domestic production. Battery is a single most important component for this electric vehicle. India does not have any known reserves of lithium and cobalt, which are required for the battery production. Dependences on other countries for the imports of lithium ion batteries is an obstacle which is becoming completely self reliant in this battery manufacture sector. How do we overcome these challenges? The Indian government is working to make electric vehicles more popular in the country. The government has set up charging stations near major cities and has been made it easier for the people to charge their cars at home. And also the government is giving opportunities for battery manufacturers and the storages to provide promoting the sustainable development, considering the government initiative promotions to have a renewable power energy 450 gigawatts of energy capacity for a target by 2030. Increasing in research and development in electric vehicles, This is also one of the key factors which helps in encouraging of the technologies that are suited for the Indians for the form of both strategic and economic standpoint of view. Investment in local researchers and development is necessary to bring the prices down. It makes sense to leverage local universities and existing industrial hubs to work on developing their increase in R&D such that we could further get down the cost. I see a great potential to share my experiences and lessons learned over e-vehicles today. So what I feel is we must work together to respond and improve on the e-mobility is vital. Today's event opens a new chapter for us in helping to curb the transportation sector emission following India's carbon neutrality pledge for 2060. This would be our target for India to have a carbon neutral zero by the year 2060. And through our continued cooperation with young talents from Indian graduates, I'm confident that the road ahead will always be green. Thank you guys. Thank you guys. Thank you for all the time and support.
Thank you
I'm
very
done,
much,
Mr. Sridhar,
Mr.
sir.
Rohit. Thank you very much. With your global experience, we got good exposure. Our participants can able to identify what are the challenges related to the design and development of EVs.
Mhm.
And you have given good information about the development across the globe. What are the present challenges related to the companies and what government can do related to the development of these EVs. Thank you very much
Yeah.
for sharing your views and experience on EVs.
It's my pleasure.
Thank you
It's my
very much.
pleasure.
Hope we will have fruitful interactions in future also. Thank you very much,
Looking
Mr. Rohit.
forward. Looking forward, sir. Looking forward.
Thank you very much. Now I am inviting Dr. Krishna Kumar sir to deliver his lecture. Before that one, I want to speak a few words about him. Dr. Krishna Kumar sir completed his BTech from NIT Bhopal in electrical engineering, MTech in power systems, and PhD in electrical engineering from the same institute, NIT Bhopal. Very few people get this opportunity to complete their education in the same institute. Then they will get good familiarity related to the activities of this institute. In that aspect, I am congratulating Dr. Krishna Kumar sir getting 3 degrees from NIT Bhopal. Now, SAR is with Thapar Institute of Engineering and Technology, formerly Thapar University, Patiala. It was founded in the year 1956, a really old institute. Was the first institute which got NBA accreditation in India. Next one is PhD Technology Coimbatore. And SAR is from a prestigious institute, Thapar Institute of Engineering and Technology, Patiala. SAR has research interests, topologies and control schemes of multi-level inverters, power converters for renewable energy applications, fault tolerance power converters. And SAR has more than 60 SA high index citations. And SAR are the contributed books also, multi-level converters, conventional and emerging topologies and their control published by Atomic Press Elsevier. And he has Indian patent also, Cascade multi-level inverter. And he has good achievements, awards and recognition also. He got Young Scientist Award in 2015 conferred by MP Council of Science and Technology, Government of Madhya Pradesh, during 30th MP Young Scientist Congress held at Bhopal during 2015. Then CAA Award for Excellence in Teaching 2016 conferred jointly by Confederation of Indian Industries, CAA, and Sagar Group of Institutions in the year 2016. He is Mentor of Change selected as Mentor of Change by NITI Ayog Government of India for Atal Tinkering Labs under the Atal Innovation Mission during 2018. He has delivered many expert talks in the short-term training programs and faculty development programs. In the last series one, SAR is one of the speaker, and SAR is agreed to take up one more section today. I am welcoming Dr. Krishna Kumar sir for his talk on electric vehicles, particularly in power technologies. Thank you very much, sir. Please start your section, sir.
Thank you very much, sir. A very good morning to all of you, sir. Am I audible?
Yes, sir, you are audible, sir. Clear,
Yeah.
sir.
Thank you very much, sir. Can I start sharing my screen?
Sir, please share, sir. Please share the screen. Screen is visible, sir.
Okay, thank you. Thank you so much. I welcome you all to this session, which will be focusing on the advances in power technologies for electric vehicles. Just now, Rohit sir has very beautifully and very succinctly, he has summarized all the opportunities and challenges that we face for the penetration of electric vehicles, especially in the context of Indian scenario. So I want to thank Sridhar sir and the team behind him working for the organization of this online FDP on trends and challenges in the development of electric vehicles and hybrid electric vehicles. Selecting a topic for this talk was very difficult for me because although I am working on the area of electric vehicle charging and electric vehicle drives for some time, but uh, I faced a challenge because this is being organized by the Department of Mechanical Engineering. So I had a feeling that many of the people joining this FDP will be from the mechanical background. But the time has come that the boundaries of these branches, they are blurring very fast. So we need to take up this challenge. We have to understand that an interdisciplinary approach to uh, development of such technologies will only be sustainable in future. So to start with, like right away, I would start with this quote, my favorite quote, that no force on earth can stop an idea whose time has come. Electric vehicle is such a technology. Now the time has come, and we all have to, make our contributions, especially in the context of the challenges that we are facing. As summarized by Rohit sir, main challenges are in the field of uh, the raw material for battery manufacturing. India will have to look after it because we do not have any known reserves for lithium and all. So many a times when I talk about electric vehicles, the participants, they are very much keen to know the research areas which will give them an opportunity to make a very impactful contribution. So right at the beginning, like I have summarized these building blocks of future electric mobility. I do not claim to be an expert of any of these blocks, but yeah, I very firmly believe that we all can make some kind of contribution in the development of these blocks. So in today's talk, we will be talking about the building blocks pertain to uh, which pertain to the power related aspects, electric power related aspects. So just a minute. So these aspects will be mainly in terms of the challenges related to charging, that is the charging station, and electric vehicle will gain uh, sustainability only if the power which is being used comes from renewable energy sources. If we continue to burn fossil fuels to drive electric vehicles, then certainly it's not
Sir,
going
sir,
to be
please, Krishna Kumar, sir, please share the full screen, sir.
okay. Okay,
Thank you, sir.
I'm sorry. I was actually looking for just a minute. Yeah, is it all right now?
Yes, sir. Yes, sir.
Okay, just a minute. Okay. Actually, I was looking for a laser for here, but anyway. So as you can see here, like lot of technologies are going to be uh, contributing for better penetration of electric mobility. So today we'll be talking about the charging aspects, the renewables, and the impact of electric vehicles on the grid, and some emerging technologies like V2X. But in addition, as you can see from here, interconnectivity between the vehicles, between the grid and the uh, what we call the aggregators is going to be an important aspect, because this aspect is going to address the range anxiety on the part of the vehicle users. And for the grid, like it's important that the impact on the grid is minimal when there is a lot of electric charging, especially with the emergence of fast charging stations. So this is an overview like of what we are going to discuss today. And as far as the power technologies are concerned, like we will be discussing about the simplest of the technologies that can be done is a battery swapping, the charging technologies, the drives, the V2G technology, some points about wireless charging, and also I'll also share some of the research findings at my institute, done with my research group here. So, as aptly like discussed by Mr. Rohit a few minutes back, the dilemma should not continue, right? For example, here I have shown a picture where in 2017, like, and currently also, we had a dilemma of like from where to procure uh, oil, and there, like we are procuring very expensive oil, and especially like the prices of the oils are highly unstable. Any international aggression leads to a rise in the price of oils. So the actually the prices are highly unstable, the supplies are highly unstable. So in 20, by like 2027, when we target to increase the penetration of electric vehicles, we should not face the same dilemma in the respect of electrical energy, right? It should not be the case that the either the electricity is very expensive that time, or it is unsustainable due to like uh, more use of fossil fuels to generate electricity, or it should not be the case that the infrastructure development does not support the penetration of electric vehicle. So few days back, I had some kind of meeting with the people from ABB, and they are also facing the same kind of dilemma, right? The question is that the question that is being asked is the same question, like what comes first, the egg or the chicken? People don't want to purchase electric vehicles because they do not see uh, many charging stations around them, and like investors are not ready to invest in charging stations because they do not see a lot of electric vehicles around them. So where does it actually start? So that is a very important question. The government certainly is pushing a lot. There is a lot of subsidy in purchasing electric vehicles. I live in Patiala, and Chandigarh is very near to this place. So in Chandigarh, like all the parkings are free for electric vehicles. There are many incentives for the purchase of electric vehicles, but still, like uh, people are very much apprehensive about using electric vehicles because our experience with ICE engine based vehicles has been so great for the past many decades that we are used to the comforts that an IC engine based car offers, especially in the terms of the dynamic response in driving the car, and like the quick refueling that we can do with an IC engine based car. So this is a very important challenge for to have such kind of infrastructure we can actually support, which can actually promote the purchase of electric vehicles in India. So This is some of the automobile sales data. These are combined data, like electric vehicles. They have picked up trends only in the past 2 or 3 years. But you can see here, like in 16-17, like in India, like a total of around 2 crore vehicles were sold, including three-wheelers and two-wheelers. And you can see that there is a growing trend of the sale in vehicles, right? As the living standards are rising, and as the developments in technologies, they are enhancing the use of vehicles for many purposes, like food delivery, and there are many things which have strengthened the ecosystem for mobility. So naturally, this trend is like going to maintain itself. And as Rohit sir said, that 30% by 2030, India is targeting to have 30% of the vehicles as electric vehicles. So it's going to be a huge challenge and a huge opportunity also. Now, as far as electric vehicles are concerned, these are some of the uh, top selling, I would say, uh, vehicles worldwide. And here from the technical specifications, we can see that many manufacturers are offering different ranges of battery voltages. For example, you see for uh, a very like starting kind of car like Bolt, it has a battery voltage of 350 volts, whereas Porsche is offering a battery pack which works on 800 volts, mainly to support fast charging. So this is another challenge because standardization has to be there for EVSE manufacturers, especially like in India. If you see, these are the top selling models now. Tata has been a pioneer, and the battery ranges, they start from 72 volts, they go up to 400, and probably like manufacturers, they are working on higher voltage ranges also. So power technologies for electric vehicles, which is the main topic of today's discussion, is focused on this point also. A wide range of voltages, a wide range of capacities, a wide range of the driving ranges. So it has overall, the mix is very much confusing, very much uh, it has got a lot of, you have to make any product, you have to see what kind of target you want to achieve with these very wide range of specifications. So why electric vehicle? Like we all understand that burning a lot of fossil fuels is not in our interest. Uh, Technically, if you see the energy consumption uh, per unit, distance, if you see, we see that that kind of energy consumption is very less in electric vehicles as compared to that in IC engine based vehicles. So overall efficiency achieved from an electric vehicle is high because you are using electric motors as against the IC engines. But another challenge is to see the overall efficiency if you need to consider the grid also in the picture. So here I have shown, the energy efficiency of electric vehicles as compared to the IC engine based vehicles. You see, if you use crude oil to generate electricity, which of course in India we do not do, but this is just to gain a perspective. Then we see that like in the power plant, in the power transfer, the transmission and distribution system, the charging of the batteries, and the efficiency of battery itself, that has actually less efficiency if you use that refined oil, the gasoline, directly in an IC engine based vehicle. So either by burning fossil fuels or by using other means to generate electricity, is not going to be very sustainable unless we switch to renewables for the generation of electricity. But like India is focusing a lot, in the past many years, we have added a lot to the renewable energy based power generation, especially uh, in the context of solar power. But a challenge which is being faced by the electrical engineers, especially from the grid point of view, is that these photovoltaic based power plants, what we call as distributed generation, the small power generators, they are kind of invisible to the grid. The grid does not know when the power is pumped to the grid from these sources, or when these distributed generators, which are also in cases acting as a load there, are using the power. So that kind of invisibility is very challenging for electrical engineers. So the increased penetration of electric vehicle also incorporates a challenge of power generation. We are targeting renewable energy based power generation. We are targeting a distributed generation. So actually this challenge is a multifaceted challenge. It is not just about the electric vehicle. It is also about the interconnectivity of the vehicles and the power which is to be generated for the purpose. So this is a typical structure of an electric vehicle. I have taken into account the um, power needs of a vehicle, right? So uh, as we know, the vehicle is run by an electric motor. We will have a look at the kinds of the motors which are used. And this motor is run by a battery, high voltage or a low voltage battery, as the case may be. So the battery gives you electric power in the form of DC, and most of the electric motors, they require some form of AC to run. So there has to be an inverter which can convert that DC into AC. In addition, like to match the DC link voltage at the inverter side with the battery voltage, we need a converter, right? So this is the main power circuit which runs the motor. To charge this battery, you need a battery charger. Battery charger can be an onboard charger, which is like there in the motor, in the vehicle itself, or it can be an off-board charger, what we call as a charging station. To run the ancillary loads, like which mostly work on low voltages, another DC to DC converter, for example, for the power windows and all. So there is another DC to DC converter, and there is a low voltage battery bank also to support the ancillary loads. Now, as I was talking about the use of the absolute requirement of renewable energy based sources to generate electricity for EVs to sustain, it becomes important to understand that the photovoltaic based power generation is highly intermittent, because in the daytime, you have light to generate power, but at the night time you do not have the light. And even in the daytime, like as the temperature changes, as the illumination changes, the power production from the PV source, it changes. So PV based power generation is highly intermittent, and to overcome that intermittency, we need to store the power when it is available. Now storage is mainly done in batteries, which are very expensive, right? You can see, like when you install a solar power plant at home, if it is grid connected without battery, then the cost is very low, but if it is grid connected with battery, the cost is very high. So storage of that power is a big challenge. But the electric vehicles, which are acting as loads for the grid, can actually become a storage device because of the batteries inside the vehicles. These are large capacity batteries, and they can be used as storage devices for the solar power which is generated whenever it is available. So when I say that the renewable energy based power generation is the key to make electric vehicles sustainable, then here we see another side to it, that the electric vehicles, they can act as distributed kind of energy storage devices for the intermittent photovoltaic based power generation. So what we can say is that EV and PV actually they are made for each other. So for that to happen, the electric vehicle should be able to transfer power back to the grid whenever the grid whenever the grid needs it, right? So here the converters which are shown here, they are bidirectional in nature, which means that the power from the battery can flow back to the grid. So this is known as V2G, from vehicle to grid. So we'll talk a bit about this, but the main point here is that EV and PV is a kind of made for each other solution, and they can greatly support one another. So coming down to apparently the simplest uh, possible technology to drive electric vehicles is battery swapping. So in battery swapping, what happens is that you use your vehicle and the battery gets discharged, and you take it to a station, and there they swap the battery with a charged one. Now the solution looks simple, but actually the application uh, is like going to be very complicated, and mm, in some cases, like in Europe, you can find that, like for e-bikes, for the small bikes, this kind of solution is highly effective. This kind of solution can also be very highly effective for very large vehicles. But at the same time, for large vehicles, like fuel cell based technology is also highly effective. So there is a lot of hit and trial which is going on. But if you can have a simplified kind of classification for battery swapping station, then this is what I have shown. Like, one kind of classification can be based on the type of automation, because we are targeting that the user experience should be as quick as like the user experiences when she's using an IC engine based vehicle. So overall experience of using an EV should also be similar, right? So if the automation level is very high, which does not require any human labor, then the user experience can be very, smooth and very quick. But yeah, as of now, because we do not have a lot of penetration of electric vehicles, most of the battery swapping stations will be manual in nature, right? So human operators need to operate. Now, according to the battery pack unmounting direction, now this is again a very big challenge, because there is no uh, uniform kind of understanding between the manufacturers, right? If any, like battery swapping is not on the top of their mind when the car or any electric vehicle is being designed. So swapping, the mechanical kind of swapping, the unmounting direction is another challenge. So it is the possibilities are side swapping, bottom swapping, top swapping, and front swapping. I'll show you some examples of bottom swapping, which is being actually used in China. So this is going to be a very exciting uh, field for mechanical engineers, especially because the design itself, at the early stage, the design itself has to take care uh, of this aspect, whether the vehicle is going to support battery swapping or not. If it is going to support battery swapping, then the exact amount of automation level and exact kind of uh, the unmounting of the battery has to be taken care of. Now, according to the swappable electric vehicle type, again, it can be a classification, because for passenger cars, the batteries are small. The effort of removing and replacing the batteries will be lesser as compared to for heavy trucks and buses, right? So this can be a classification of battery swapping. Now, another important thing is that even if we swap batteries, which makes the overall user experience very good, if it can be done very quickly, still the batteries which are taken out from the vehicle are to be charged, and you cannot again like take a lot of time for charging, because otherwise you'll have to make a lot of batteries for these. So from the point of view of like charging these batteries, we can have another classification where you can have a centralized battery charging station, or you can have a distributed kind of battery charging station. So what is happening here is, like in centralized charging station, like you have a huge number of batteries. Here you can incorporate uh, the renewable energy based power generation, which is connected with the grid, and the batteries can be charged and they can be sent to a subsidiary kind of charge swapping points where these batteries can be swapped. Or you can have a distributed kind of charging infrastructure where not huge amounts of batteries are charged at one charging station for these swappable batteries. So this is one kind of possibility for architecture of the charging stations for the batteries which are to be swapped. Now, as compared to like fast charging stations, uh, when you talk about the centralized battery swapping or the distributed battery swapping, you have to certain trade-offs are there, which are like to be seen. For example, compatibility of the electric vehicle, as I was talking about, like the batteries. Like it's not the first thing in the mind of a manufacturer to have swappable batteries, because each manufacturer has their own preference of the battery voltages, of the battery type, the kind of a cost they are going to put into the batteries. So swapping is it becomes very difficult when the ratings are not uniform. So compatibility is a very big challenge as far as swapping of the batteries is concerned. Whereas when charging of the batteries, like the compatibility can be very high. As we'll discuss it at a later point, how this compatibility is so high. So in different aspects, like we can make a comparison between battery swapping and fast charging. But the main concern is the last point, the impact on the grid. Now, because like when you're swapping the batteries can be charged at your will. When the load on the grid is low, then you can charge the batteries. But fast charging uh, creates a lot of impact in the grid, because you're extracting a lot of power from the grid to charge the batteries in a charging station. No, I'm not talking about the battery swapping. So it's a very big challenge for electrical engineers to monitor and to contain the impact of fast charging. For example, if a charging station extracts 1 megawatt of power on a highway, if number of vehicles are charging, like some of the manufacturers, they allow the batteries to be charged at 250 kilowatts. So if 4 of such cars are being charged at a fast charging station, drawing 1 megawatt of or 0.1 megawatt of power, then it is going to create a lot of impact on the local grid. So this has to be contained, it has to be monitored by the grid operators. So this is a challenge. From this point of view, from the grids, the impact on the grid, battery swapping looks to be a very good alternative here, because the batteries can be charged at will. Also, like this is an architecture of the possibility of an architecture of battery swapping stations. So now from here also, like although it appears to be very simple, that batteries can be swapped in a car very easily. But from the point of view of functioning, we see that a number of subsystems are required for the fast swapping and uh, for safety of for safety and for transferring those batteries for charging. So a number of like back end operations will be involved, right? So it's not going to be directly to be so easy. So battery swapping, like when we are talking about like unpacking that, taking out the batteries and all. So many possibilities are there. One possibility is shown here where you are when the battery is positioned at the trunk, and you can directly take it out from that part and you can replace it. Or some kind of uh, system can be there when the battery is positioned under the chassis, and it can be taken out um, from the car and it can be swapped. So but once again, like this has to be conceptualized at the manufacturing level of the car itself, because retrofitting it with some kind of this kind of system is going to add to the costs and inconvenience, and certainly it will change uh, the such changes, like if they are not carried out by the original manufacturer, then the user experience may not be so good. So these are like some swapping stations. I have shown one swapping station. This is at in Beijing, and this this here they take out the batteries from the bottom of the vehicle here. Uh, Probably you must be knowing that Caterpillar has electrified large dumpers also, uh, very latest development. So in especially which are used in iron ore mines and all. So battery swapping for these heavy moving vehicles is a very good alternative as compared to charging those batteries with uh, fast charging stations. Now, like as far as battery swapping is concerned, like certain standards are also need to be followed if it is going to be harmonized between like the batteries of various in various electric vehicles. So these standards may pertain to um, the basic foundation and general like systems and equipment, uh, the power batteries, the interfaces, both kinds of interfaces, the power interfaces and the communication interfaces, and operation and service networks, peripherals, accessories, and all. So a complete set of infrastructure standards has to evolve for to make battery swapping a very widespread like kind of happening in India. Now, battery swapping seems to be the like uh, the option with the least effort, but as we saw that it will also involve a lot of backend operation, and the effort is going to be high. So what I have shown here is a typical onboard charger. Onboard charger, as the name suggests, like it's there in the vehicle itself. So what you do is that you connect the inlet to the grid. It most of the times it is a single phase AC input, and we can see various stages of power conversion here. So what happens is first the AC is converted to DC. Some kind of galvanic isolation is required for the protection of the user, which means that the battery should be electrically isolated from the grid. So that kind of isolation either comes from the DC to DC side or the AC to at the input itself. Like we can have some kind of transformer, but that transformer will be a low frequency transformer. So most of the manufacturers um, they prefer to have a high frequency transformer, which means that the transformer has to be at the DC to DC conversion stage. So in this diagram, like we see that the AC is first converted to DC, the low frequency AC. Then this DC is converted to a very high frequency AC of the range of 20 kilohertz to 1 megahertz. This high frequency AC is then transferred to the other side. This is a high frequency transformer in between. And that high frequency AC is again converted back to the DC, which is used to charge the batteries. Now at the front end side, a power factor correction converter has to be there so that the power, because the overall circuit is a non-linear circuit, so the overall power drawn from the AC side should happen at unity power factor. So this is the basic block diagram, a typical structure of an onboard charger. A company called UTK, it has designed a very high power battery charger. This is 22 kilowatts charger. And as you can see, the size of this charger is like very impressive. It's very small, mainly because it uses very high frequency switching, due to which the magnetic components, like they're very small here. So this DAB is the dual active bridge, and the DAB actually uses the high frequency conversion that I was talking about. It is incorporated in the DAB itself, in the form of a high frequency transformer. So you can see the high frequency transformer is very small here because the size of the core is small. If you compare it with a low frequency transformer, then the size of core will be huge. It will add to the weight and volume of the charger. So my only intention here is to show that these onboard chargers, though they support a lot of power, but the sizes can be very low if right kind of power electronics technology is employed. Now, one challenge that is faced here is the kind of power that you can draw from the points available at home. So if it is a single phase point, then there are limitations that the amount of power that you can draw. And similarly, for a three-phase point, you have different kind of limitation. So that is the only limiting factor here. Power electronics can certainly support very high power, high values of power transfer in very small sizes. So this kind of charger, the characteristics are very interesting here. You can see in the x-axis there is the amount of current, the charging current, and the voltage. So it starts with large charging currents when the battery is experiencing low state of charge, and from so this is a very good IV characteristics of the battery, a battery charger. Now, as far as like other manufacturers, I'll just give you an example of one onboard charger, but like many other manufacturers, they are coming up with very large values of power, which can be transferred in the onboard chargers. So you see, like up to the power of 350 kilowatts or even more can be put for the vehicles, and there is a wide range of powers, which power ratings which are being these capabilities which are being incorporated in the vehicles. So again, there is no standardization here, and the manufacturers, like they're incorporating these charges, they are providing their own charges, they are incorporating the battery technologies based on the kind of performance that they want to achieve. Now, this is a simple representation of an extreme fast charging station, XFC. So here the battery gets charged uh, by very large amount of powers in the range of 250 kilowatts to 500 kilowatts. So in such scenarios, like energy storage becomes very essential so that the grid is not hugely impacted by extreme fast charging. And in many of these cases, like we use low frequency isolation between the grid and the batteries, because the technology, because the real estate will be of not much concern. You are using a charging station here anyway. So the the conventional transformers can be used here. This is a modular kind of design using a multi-level inverter for extreme fast charging. My only intention here is to show some technologies which can be used to make extreme fast chargers. Another interesting kind of technology is uh, the use of the um, power transfer in inductive whenever power is transferred using an inductive coupling. There is no actual interconnection between the primary side and the secondary side. So what is typically known as wireless charging. So wireless charging has come up as a very interesting kind of technology for enhancing the user experience. So this is a typical structure of a wireless charger, which shows that the left part of the circuit is inductively coupled with the right part of the circuit, right? So LP is the primary side, the inductance of the primary side, and LS is the inductance of the secondary side. And the coupling between them depends on many factors. The main factor is the distance between the coils. So this has actually become a reality. Like a company called Vitricity has launched these chargers which can charge your vehicle with a wireless kind of connection. Now many users find it to be very safe as compared against the uh, wired charging, which is normally done in electric vehicles, right? So here the only thing is that the transmitter coil and the transmitter coil is outside the vehicle, the receiver coil is inside the vehicle. So unless it is provided by the vehicle manufacturer himself, then some kind of retrofitting is involved here if you are purchasing this kind of charger from a third party. So the vehicle should have some kind of provision to support such kind of retrofitting. Here is another scene. Like Hevo is a company, China based company. So this is a manhole like charger, again wireless charging. Momentum is another company which makes such chargers for electric buses, wireless charging for the buses. Plugless power is another like entity which makes wireless chargers. So numerous like manufacturers, they are coming up with their own technologies. And again, there is no standardization here. But wireless charging seems to be very exciting because for the user, like it appears to be very safe because the car does not come in physical electrical contact with the grid. So here is a small comparison between the chargers that I've shown here. The main thing here is the kind of the power transfer that these chargers are able to manage. So the wireless charger from Momentum can manage up to 200 kilowatts of power, which is very, very impressive. And not just that, the air gap, the gap, the distance between the transmitter coil and the receiver coil is 610 millimeters, which is a very good kind of, distance. So still a lot of work is going on on improving the designs, on improving the efficiency of wireless chargers. So for wireless power transfer, this is a snapshot of the state of the art. The universities are working, research laboratories are working on it. Of course, the industry is working on it. So Zurich, ETH Zurich in 2016, they showcased this kind of high power density charger, 160 kilowatt per meter square with an efficiency of 95.85%, which is impressive because you have to transfer power through the air gap. So, like different kinds of technologies are being incorporated. Some of them are using, a direct dual active bridge based technology. Some of are even using switched capacitor based technologies for wireless power transfer. But this is an interesting area where a work can be carried out. Now, as I was talking about the V2G scenario, where when we talked about the EV and PV being made for each other, it automatically brings into uh, context the vehicle to grid technology. So for V2G, it's not only going to support the photovoltaic, intermittent nature of photovoltaic based power generation, but actually it's also going to enhance the performance of the grid. Like here in the upper part, you see for various charging scenarios, when the grid experiences a morning peak and an evening peak, and like if at that time the extra demand from the EVs is going to, further the at that time. Now in V2G can actually flatten the curve of this demand. During the morning peak, the power from electric vehicles can be released onto the grid. During the daytime, when you have a lot of sunlight and the PV-based power plants are working at their maximum production, at that time you can actually charge the cars. And again, like in the evening time, these cars can operate on V2G mode, and uh, they can support the grid. So the blue colored part here is the power which is drawn from the grid, and you can see that in the bottom curve, like the demand which is being fulfilled by the grid is reduced. So here, like we see that the electric vehicles, they not only they can always act as source loads for the grid, but they can also act as sources, right? And it's a distributed kind of energy storage scenario. And the good thing is that the grid operator or the agency does not have to uh, invest on batteries, which are very expensive. The investment on the batteries is done by the vehicle owner. So it is a distributed kind of scenario. So the investment by the EV owner also is very less actually. But for V2G to happen, like we need to have bidirectional kind of power flow at all stages of the interconnection between the grid and to the electric vehicle battery. As of now, like in India, like the battery management system does not allow V2G as of now. But we are sure that the states will quickly come up with their own policies. So here I have shown like an example from the Netherlands where the V2G technology is being actively employed by a fleet owner called V Drive Solar. So what do they do is that they 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 use solar power to charge the batteries when the sun is out and open and it's shining, and they support the local grid during the times of peak demands, right? So that's how they earn credit, they make money, and in the rest of the times, like, they rent out these vehicles. Again, the same city, like, we were talking about what comes first, the egg or the chicken. So we need to have, this kind of infrastructure, the charging infrastructure, which can actually encourage the vehicle owners to go for electric vehicles. Now for India, the Ernest and Young, they had done one consultation for the government of India, and they suggest that in the highways, like, in for every uh, 100 kilometer, if you have a fast charger, then it can hugely support the use of electric vehicles. Now, like, we had one meeting with ABB, and we were working on some statistics. So in a big state like Madhya Pradesh, they have around 10,000 kilometers of highways, the state highways and the national highways. And if one charging station costs you 10 lakh rupees, and if you are to install one charging station per 100 kilometers, then like, in a cost of 20 crores or so, you can uh, have lots of charging stations throughout the uh, these highways in a state. So if with that kind of planning, we can encourage, the government can encourage, or even the private investors can encourage the users to go for electric vehicles. Of course, the user is also, like, concerned about the um, overall cost of owning an electric vehicle. For example, what happens when you got to change your batteries after 10 years? The batteries are expensive, and if if you are to change the batteries every few years, then it is certainly going to add to the costs of, like, owning an electric vehicle. So from the point of the infrastructure, from the power system infrastructure itself, like, if we are going to target, like, 70% of the cars to be electrified by 2050 or 2060, then around 30 million EV charging points are going to be added, and electricity demand will go up by 70%, right? So uh, our grid, like, it can support such an increase in demand, but the only problem is how to get this electricity to people for them to charge, which means we need physical infrastructure. We can manage the electricity itself, the increased amount of electricity which is required, but we need physical interfaces at which are properly distributed throughout the country, where people can go and connect their electric vehicles. So that is going to be a huge challenge for India to uh, to add on to the network, so that we can increase the number of charging points. So this is a challenge that the infrastructural requirements is going to face. Now, the relief in this scenario is the price of the battery. Here you can see the lithium ion battery pack. The prices have fallen from 900 US dollars per kilowatt hour to the current scenario of around 100 US dollars per kilowatt hour. And the range is also has shown a lot of, like, increase from 150 kilometers to 400 kilometers. So this is a very encouraging scenario, the lowering costs of the battery and the increasing ranges. But again, like, we are going to depend on uh, for lithium, for these minerals, because we do not have known reserves in India. So that is going to be a challenge. As far as charging power is concerned, again, like, for various uh, battery packs, most of the manufacturers, they are using lithium ion battery packs. So the charging power has gone to very high levels, to 300 to 500 kilowatt which certainly means that like we can support fast charging in the vehicles, right? To help the user to overcome the range anxiety. Now, from the infrastructural point of view, galvanic isolation is going to be uh, a mandatory requirement for all kinds of chargers. So, as we were discussing, like you can have low frequency isolation at the AC side, or you can have a high frequency isolation at the DC to DC conversion stage. Now, when you are going to have a high frequency isolation at the DC to DC conversion stage, then the size of the core will be less, but the material which is used for the core is a bit brittle as compared to the CRGO's silicon steel that we use for low frequency transformers. So for high power applications, like manufacturing these kinds of cores is very challenging because this material is brittle and you cannot easily shape up this material for the core. So this is a big challenge for that. Now, as far as the requirement of power electronic topologies is concerned for the charging infrastructure, you need basically you need AC to DC conversion at all stages when interacting with the grid, and as because we are the requirement of V2G is going to be an absolute essential. So these all have to be bidirectional in nature. So the typical topologies required will be AC to DC conversion, which will need to perform the DC to AC conversion as well, without isolation, of course. But you need to have DC to DC conversion stages with and without isolation, depending on the type of topology that you are employing. Now, this is the kind of onboard charging which is made by Coastal. So here you see the topologies which are used are very simple. In here, this is of course unidirectional in nature because in the output side you have a bridge rectifier here, simple bridge rectifier. But the simplicity of this topology and the efficiency is highly encouraging here. Similarly, like for high power charging infrastructure, for example, this Porsche, which can support a power output of 360 kilowatts, which is huge, with an output current of 500 amperes. So again, like the structure here is very, very simple here. And efficiency is also very much acceptable of 95%. So charging infrastructure has to support both onboard charging as well as fast charging, offboard fast charging, for better penetration of electric vehicles. So I'll be discussing more about the multi-level based charging a little later. But just to give you an idea, like the megawatt charging stations will require some kind of modularity, so that we can easily add on to the modules, or we can easily repair such high powered charging stations, which automatically means that uh, multi-level converters will play their role. Now coming to the inside of a vehicle, a lot of power electronics is involved uh, in the vehicle. This is a very simplified representation of the electric vehicle train, the power train, where you have the battery pack, you have an electric machine, and in between there is a traction inverter which converts this battery power which is obtained in DC form to its AC form. Now for regenerative kind of braking, like reverse action will take place when the motor will act like a generator. The mechanical energy stored there as kinetic energy will be converted to electrical energy with the machine acting as a generator, and This converter, the inverter part that I told, will actually act like a rectifier, and it will charge the battery pack. So this arrangement has to be bidirectional for an optimal use of power. But this is the simplest possible uh, representation of the powertrain for the electric vehicle drive. Now, once again, like when we talk about electric vehicle drives, numerous types of machines can be used for powering the wheels. The typical technologies, the classification is shown here. You can use brushed motors, or you can use the brushless motors. So we all know, like, the brushed motors are the DC motors, which can be series or shunt. They can be self-excited or separately excited. Brushless motors can be induction motors, synchronous motors, or permanent magnet brushless motors. So from the point of view of the drive, numerous motors are available. Different manufacturers are using different types of motors. For three-wheelers, mostly brushless DC motors are being used. For cars, like Tesla uses induction motor drives. Tata uses permanent magnet synchronous motor drives. So there is a lot of debate on their advantages and disadvantages. The power density offered by a synchronous motor, permanent magnet synchronous motor drive is very large. But since it requires permanent magnets, so that again, that dependency factors come into picture. Induction motor is highly rugged, but the overall efficiency achieved from an induction motor is less as compared to that of permanent magnet synchronous motor drive. So again, like, it will depend on the type of experience that a manufacturer wants the user to have, that the EV drive will have to be finalized. So especially for different types of terrains where the variation in terrains is very large, induction motor drive is, of course, uh, it works well. So this is the combinations of different technologies from the point of view of the electric machines and from the point of view of the battery technology. Of course, lithium-ion batteries are leading this whole the pack of the batteries here, the battery technologies. So this is also, like, verifiable from the data, from 1884 to 2016. If you see, you can have a look at the types of motors which were used. So the DC motors have been very prominent for vehicle drives, mainly because the simplicity of the control that can be used. Speed control can be very easily achieved with DC motors. But with the emergence of power electronics, we see that induction motors can be, again, they can be controlled. The speed control can be very effectively done, as good as that of a DC motor, and hence the induction motors are now being used very prominently in uh, traction, in even in, like, locomotives and in electric vehicle drives. But the major gain has happened, has been the major lead is taken by the permanent magnet synchronous motors, because the power density is very high, and the improved power electronics can help to achieve very effective control of a permanent magnet synchronous motor. So if you see the overall share of the motors till date, the 64% of motors used in electric vehicles and hybrid electric vehicles is captured by permanent magnet synchronous motor, and a large portion is a distribution between DC motors and induction motors. Switched reluctance motors, of course, a lot of research is going on for very large speeds. Like, switched reluctance motors are highly effective, but overall control, overall power density, and overall um, speed torque characteristics are to be well organized, well controlled for an electric vehicle. So once that challenge is overcome, then probably synchronous, this switch reluctance motors will also gain a lot of traction. In the past 10 years, so that was a scenario of past many years. But in the past 10 years, if we see 80% of the motors which are being used for electric vehicle drives are permanent magnet synchronous motors. 17% are induction motor. The major advantage again here is the induction motors. We have very well established, control technologies for induction motors, and they are very rugged, and the performance wise they are good, but only thing is the efficiency is on a lower side as compared to a permanent magnet synchronous motor. Also for the batteries, we can see that the lithium based batteries, they have gained a lot of momentum in the past 2 decades as compared to the other technologies. And of course, lead acid batteries, they as well as nickel based batteries, they had some percentage of usage, but the major percentage of usage in EVs from 1884 to 2016 is captured by the lithium based batteries. Now a very interesting kind of technology is being offered by some manufacturers, where they use the windings of the machine for both the purposes, like for the charging purposes when the battery is to be charged, and for the traction purposes, of course, when the uh, mechanical power is required. So if you see this overall circuit, when the machine has to work, then when you have to drive the vehicle, then this converter will act like an inverter here. It will draw power from the battery and the machine will run. But when you have to charge the battery, then when it is connected to the grid, then along with the machine windings and this inverter, they will play their role for the power to flow from the grid side to the battery side. So these integrated chargers are very popular because they add to the compactness, to the power density of the overall system installed in the vehicle. So what should we expect from the power system and the charging infrastructure is some kind of contribution from all the sectors, right? From the manufacturers of the EVs, which allow the BMS from the power sector to incorporate a large amount from the renewable energy based power generation, and from photovoltaic and wind and all, and from an interconnectivity point of view, so that they can you know uh, communicate with one another, so that the utilization of power is optimum. So this is what is expected from the grid. Now this was the overview of different power technologies. We talked about the batteries, the battery technologies, and the battery swapping, if it is possible in Indian scenario. We talked about the charging scenario, the onboard chargers, the offboard chargers, and fast chargers, extreme fast chargers. We talked about uh, the drives, the electric vehicle drives, the emergence of different kinds of motors. We also talked about the scenario where the charging and drive part is integrated, where the machine winding can it takes part in both the discharging of the battery and charging of the battery. So this was a short overview on the power technologies and the advances, especially with respect to electric vehicles. Now, from here, this point, I'll give you two examples of some kind of research that we have done here at Thapar Institute. One example I have taken from the charging point of view, a charging station, and another example is I have taken from the drives point of view, the machine which is a power converter, the motor in the electric vehicle. So before like moving forward, like please feel free to have any kinds of questions based on what we have discussed till now, or any comments you may have to share with me. Sridhar sir, is it all right to have some kind of discussions at this point? Sir, am I audible? Daniel sir? Okay, so if you have any points to make or any like questions, we can discuss, or I can move forward and I can, we are left with, okay, I'll continue. So we are left with a few more minutes. Yeah. So for the charging infrastructure, like the major classification is in terms of the onboard chargers and offboard chargers. Onboard chargers can be dedicated AC chargers or the integrated chargers. One example that I had given. Offboard chargers, again, the standard AC and DC chargers or battery swapping or wireless charging. So there are certain, standards which are being which have emerged in the past few decades for AC charging as well as for DC charging. But again, there is no uniformity between these standards. This I had already shared. This is a challenge, like the wide range of voltages. This is a very big challenge for the charging infrastructure because it has to cater to a wide range of battery voltages. So if you see from Tigor 72 volts to Porsche 800 volts, there is a wide range of, DC output which has to be managed by a charging station. So based on, what we have discussed till now, a typical EV charging should have, power factor correction because you have to draw power from the grid, large amount of power, and it will always be good if it is done at unity power factor. The DC to DC converter, it has to be bidirectional again because we talked about V2G. So for EV and PV, like for them to sustain one another, it is important to have this kind of bidirectional interconnection. The output voltage range should be wide because we saw that the battery voltages in the EVs, they vary from 72 volts to 800 volts. And also, like, there should be support for both single phase and three phase, like availability of power. So based on this, various converters can be classified as rectifiers and DC to DC converters. The rectifiers can be multi-level or non-multi-level. And again, they can be boost type or buck type rectifiers. So this is a development like which I'm sharing with you. Most of the rectifiers which are used for unity power factor correction at the AC side are boost rectifiers. But actually the buck rectifiers are more suitable. The technology so far are mostly boost rectifiers. So one development I'm going to share is the development of buck rectifiers here at the our institute by my research group. So like for some of you who are not from the background of electrical engineering, what we are talking about here is power electronics. So power electronics is a technology which deals with the conversion and control of electric power, which means that we are dealing with the conversions between AC and DC powers, either from AC to DC or from DC to AC or from AC to AC or from AC to DC side, right? So this type of conversion is done by using semiconductor devices. These devices use uh, these devices, they operate as switches, either in on state or off state. We all have heard about the devices like transistors, BJTs. So BJT has many regions of operation: the linear region, the cutoff region, the saturation region. So when you use the BJT in its linear region, then that technology is called linear electronics. But when you use it either in saturation mode or cutoff mode, which means that either an on switch or an off switch, then that thing is known as power electronics. So what we are doing is we are using these devices as switches, right? So this discussion is actually a discussion on power electronics. So from the point of view of a drive, this is a work which was recently presented by us in a conference called IECON. This was the 48th annual conference of the IEEE Industrial Electronics Society held at Brussels. So this was a work presented in Brussels by us, basically for an electric vehicle drive, because in most of the cases the battery is of low voltage, like we saw 72 volts is a low voltage battery. The motor which is to run on that voltage is, it has to be enhanced by a boost converter. So what we did here is that we came up with a boost inverter which does not require any inductor. It works on a switched capacitor. So this topic, I'll explain it a little bit. So this is an inverter because it has to run a motor in an electric vehicle drive. Voltage boosting is required because the input voltage is of low value. It has to be three phase because that's how we achieve a high power density. But it has to use, not only it has to use a switched capacitor, it should not use a switched capacitor in all the legs. We presented a work which uses only one switched capacitor to obtain a boosted output at the inverter side. So this is a kind of non-inductive boosting because inductors add to the weight and volume of the overall drive. So this is a non-inductive boosting, and since only one capacitor is required, the overall count is less. So what happens here is uh, we use a switched capacitor principle, which simply means that a capacitor in a converter comes in parallel with the DC source to get charged, and then it is connected to it in series for discharge. So what happens is, because of this, levels are added to the output AC waveform. So basically it becomes a multi-level inverter, which adds to the life of the motor because the dV by dt stress on the load is reduced. Important advantage is these switched capacitors are self-balanced because you're bringing them in parallel with the battery. They are self-balanced. You don't have to add, additional circuitry for balancing. Of course, another advantage is boosting because you have charged the capacitor and you are connecting it in parallel. So if the battery voltage was, let us say, 72 volts, the capacitor voltage will also be 72 volts. And when you connect them in series, the overall voltage will be added up. It will become 144 volts, right? So, but an important problem here is that when you connect a capacitor in parallel with the battery, then huge current stresses are experienced by the circuit. And most of the such topologies, they offer only single phase operation. Even if they offer three phase operation, they need DC sources for each phase, which is not, of course, always practically possible for a electric vehicle. There's single battery pack there. So the major advantage here is that you need single source and you need single switch capacitor. So I'll explain here what happens when you bring this capacitor C1 in parallel with VDC. Then huge current stresses are seen by the circuit, but these stresses can be reduced if if the capacitor is charged repeatedly to a value which is very less, which is the ripples are very less as compared to the input voltage VDC. So we'll see how this is achieved in this work. This is a structure which shows switched capacitors based multi-level inverter, but again it offers only single phase operation. Some of the structures, like they use a single battery for three-phase operation, but the requirement of capacitors is large. For each phase, they required like one or more capacitors. And many of them are, of course, non-modular, again, undesirable thing for electric vehicles. So what we have done here is we have used a single unit of switched capacitors at the front end, and thereafter there is the traction inverter which is connected to the load. So the challenge here is to modulate the switches so that, because at that three-phase inverter bridge, the available voltage now is a varying voltage. For example, when switch S2 is turned on, then the input to the bridge inverter is VDC. But if the switch SC1 is turned on, then the input to the bridge is 2 VDC. So now the bridge inverter, it experiences a varying voltage between VDC and 2 VDC. So in this work, what we did is we proposed a modulation scheme. Since the time is limiting us, I'm not going to explain the full scheme here. But what we do here is that it works something like space vector modulation, with the only difference is that we inject some states which can actually raise the voltage to 2 VDC, and there is a mathematical formulation behind it, and this is the voltage basically which we want to see here. This is for an input of 200 volts. We see that the output voltage is 400 volts. So we are seeing double gain in the output voltage without any usage of inductors here. So this is some kind of experimentation was done, and these are the experimental results of it. I'm not going to discuss it in detail. Another thing I was talking about was a topology which can convert AC to DC, but in buck mode. So I'll just show you the results so that we can have some time for questions and answers. So this is a kind of output for AC to DC conversion, where from waveform 3 you can see the grid voltage is of 315 volts or so, the peak value, but the output voltage is 200 volts, the DC voltage, which can be used to charge the battery. So this kind of conversion is known as a buck conversion. So we've this these experimental results, they show that you can have a varying range of output voltage, which can subsequently be used by a DC to DC converter for charging the battery. Even in under dynamic conditions, like the structure works well, but I'm not sure whether we can have a full discussion on this topology. But again, like I'm showing you back the same slide that I had shown at the beginning. Lot is to be done for the better penetration of electric mobility, especially in India. We saw some challenges. Something as simple as battery swapping, it itself it offers a lot of challenge to both the manufacturer and the service provider. From the point of view of the grid operator, the upcoming charging stations is a challenge. The power which is produced using fossil fuels is a challenge, because unless we incorporate a lot of renewable power, then there is no point of using electric vehicles. Of course, electric vehicles and photovoltaic based power generation, they are made for one another, and for that V2G has to become a reality in India. And like there's a lot of research going on, V2H also, where you can use your vehicle battery to power your home when the power is not there. Smart charging is like another area where you can work. And of course, on the right side, all the area is related to interconnectivity between the vehicles, between the vehicle to the grid, to the charging stations, and analysis of the data for an optimal use of electricity and an optimal experience for the EV user, where like the user does not experience lot of range anxiety. So this is all from my side. I think we are left with some time for questions. Daniel sir, are you there?
Yes, sir. Yes, sir.
Yes.
Very well, sir.
Yeah. So sir, this is all from my side. So if there are any questions, we can take up those questions or some comments from the user, from the participants if they have.
Thank you, sir, Dr. Krishna Kumar, sir.
Sir, my sincere thanks to you for
Okay.
giving me this opportunity, sir.
Dear participants, sir is complete his section. Please put your queries. You can directly interact with Dr. Krishna Kumar, sir.
So if any participants would want to speak, you can please use the hand raise option so that we can unmute you. Please use the hand raise option so that we can unmute you. Dr. Sangeeta, can you please post your query?
Hello, Shiv Kumar, sir.
Yes, sir.
Sir, I came to know that one of the organization,
Yes, sir.
EMB electric industry, Mumbai-based company, is launching micro electric vehicle, PMV, with a weight of 550 kgs.
Mm-hmm.
Then what factors they might have considered to reduce the weight of the vehicle, sir? They are stating that in one charge, it can travel nearly 145 kilometers.
I think I also have heard about it. Probably, if you check, the number of passengers is going to be 2, I think.
That they didn't mention, sir. It is.
Yeah, I also came across such
Uh,
a news, and when I looked into the specifications, like um, it is not a 5 or 4 passenger vehicle, it is a 2 passenger vehicle, most probably. And even if like if it is not the case, then the the main investment will be on the battery pack, because the dead weight of the battery is an important challenge.
that's why I got the doubt, sir.
Yes, sir. Yes, sir. Yes, sir.
How it can
That is a big
accommodate
challenge.
within the weight of 550 kgs.
Yes, yes, yes. That is a big challenge. So
Yes.
probably, they have invested on the type of batteries that they are using. Solid state batteries is a possible usage, but I'm not sure. Uh, in that case, the vehicle is going to be very costly.
But they stated that cost will be between 4 lakhs to 5 lakhs, sir.
Then certainly this vehicle has only
Mhm.
possibility of 2 passengers only, sir. That's how they have.
That they didn't mention.
Yeah, yeah, yeah.
But 2 passengers, Tata Nano car also, which was launched by Tata Group, it can accommodate 4 passengers. Tata Nano car, that is engine-based vehicle.
Yeah. Yeah. So it is, the car you're talking about has a
Mhm.
possibility of 2 passengers. That too,
Okay.
they're not like on a single row, but there are 2 rows. like one person is sitting at the front and one at the back. So you can think of it like uh, uh, an expanded two-wheeler with a covering. That's it.
Mm. Okay, sir.
But still, it's a good innovation. For micro mobility, it is good.
Yes, sir. That's why they named it as a micro vehicle.
Yeah.
Mm.
This is the same thing that they're, but I don't think that they have invested a lot on innovation part from the, from on batteries and on the charging and all. They have just used things optimally for two passengers. That's it.
Okay, sir. Sir, one more question from the participants.
Yes, sir.
This Audi has launched one EV.
Yes,
With
sir.
one charging, it can travel 500 kilometers, and charging will be done within 40 minutes.
Yes, sir.
And other BMW,
Yes,
it
sir.
is stating that it requires 7 hours for charging the 76.6 kWh battery.
Yes, sir.
And in Audi also, this kWh battery is there, 93 kWh battery.
Mm-hmm.
From 76.6 kWh to 93 kWh, how this much difference is coming, sir, for full charging of battery?
See, it is the amount of power which is taken from the grid and delivered to the battery.
But
That is
difference
making.
is less, sir, 93 and 76.
Yeah. So when we talk about kilowatt hour, basically that is a unit of electricity. Number of units. This is energy. Watt is a unit of power, and time is the unit of hour is the unit of time. So watt into hour is energy. So basically, energy which you are taking from the grid and you are giving it to the battery. Now, when time comes into picture, then it becomes power,
Yes,
right?
sir.
So how much time you're taking. So that the when we are rating the converters and all, they are all rated in power, right? For example, when you use the socket at your home, you have different sockets. For example, you have a different socket to run your LED TV, and you have a different socket to run your geyser or an AC. Why is it so? Because the power which is to be handled by your TV and your geyser or your AC is different. Energy, we don't know about energy because it will depend on the number of hours they are used. But power is an important factor there. So the different timings which are being taken by here is due to the power rating of the converters. So that is why, like we were talking about the onboard chargers, the offboard chargers, and within the offboard chargers, extreme fast chargers. So an extreme fast charger can deliver 250 kilowatts of power from the grid to the battery. Of course, in that case, the manufacturer has to invest a lot on the heat management in the battery, because you are delivering a lot of power to the battery, mainly in terms of current. So the heat has to be properly managed. I don't know
Yes,
whether
sir.
it is making a lot of sense to you or not, but if whenever a manufacturer is talking about time, it is basically based on the power rating of the converter. kWh is the rating of the energy which is being stored by the battery. Ampere hour is the measurement of the capacity of the battery. Ampere hour is the unit of charge. So how much charge is stored in the battery? kWh is how much energy is stored in the battery. Watt is power, the unit of power. So mainly how fast means time comes into picture. So it is all dependent on the power which can be handled.
Thank you, sir. So we have another question from the participant from Durga Devi Velusamy. He says, "Dear sir, what would be the impact of communication
Yeah, communication technology
technologies here?"
yeah, that layer is going to play a very important role if large scale usage of electric vehicles has to become a reality. Right now, like CAN based communication is used for interconnection between the vehicle and the uh, charging station. You know that the The charging station has to get an information about the state of charge of the batteries, and accordingly it has to adjust itself to send power to the battery. So CAN-based system is used, but uh, uh, that is a kind of very localized kind of communication between the user and the service provider. The overall communication has to take place between the network and the user, so that you can optimally have an idea what kinds of charging stations are available, which charging station has what kind of capability, so that you can go and charge your battery. And in fact, very interesting development is also in terms of V2V charging, which means that there is a large vehicle which is carrying batteries inside it, and you can while on the run, you can get your batteries charged from there. So this kind of networking is important between the grid and between the vehicles for an optimal use of this kind of technology. Another importantly, question that popped up here, I'll add on to this, is what is going to be the use of blockchain here? Blockchain, probably it should, I'm not any expert in that technology, but based on my reading, what I have understood is uh, for, kind of uh, a seamless experience in overall the owning an electric vehicle, blockchain can help us have a seamless kind of uh, experience, especially in the payments part. So what I'll do is that I'll share some literature uh, with the Sridhar sir, so that you can share it with the participants, where the paper specifically deals with the use of blockchain technology in electric vehicles.
Sure, sir. Thank you. Thank you, sir. And one more question from Mr. Anil Kumar Chinta. He is asking about the softwares that are used for designing concepts of electric vehicles.
See, for a system level basic understanding, you can use MATLAB Simulink, but to go into the details, the best thing will be to use software called Maxwell. Maxwell can be used to model machines, to model power electronics, and to overall electric vehicle drive. And MATLAB can be used for uh, simulating the drive, as well as the charging stations and charging infrastructure part. And for thermal analysis, for the losses which are taking place in such converters and all, you can use a software called Plex. Plecs. Plex can be used.
Okay, sir. Thank you. Thank you, sir. Another question from the participant, Mr. Nandakumar S. is asking how is the heat dissipation, how the heat dissipation will manage in EV battery? Are there any problems while charging and discharge?
See, that is actually the big difference between IC engine-based cars and electric vehicles. The dynamic response of a battery, when see, there are two things: uh, the power density and the energy density. So battery works very fine when you're taking out energy from it in a in a uniform manner. But if you want quick energy, which we say that large amount of power, for example, you have to accelerate your car to a large speed in a very short amount of time. That time, the dynamic response of the battery is very poor. It has to give lot of current. Lot of current is drawn from the battery to drive the motor. So when you draw large amount of currents from the battery, battery gets heated up. So that is a challenge actually. The dynamic response is a challenge. Similarly, if you see the converse scenario, when you want to charge your battery at a very fast rate, what you do is that you inject lot of current into the battery. Now, when lot of current is going into the battery, what you're trying to do is you are trying to enforce uh, the chemical reactions to become very fast, which generates a lot of heat. And again, dissipation of that heat is a challenge. So the balanced kind of performance is achieved when you use a hybrid electric vehicle. But again, hybrid electric vehicles are expensive and they are very complicated. All manufacturers, many manufacturers are now making electric vehicles because you just need motor, you just need battery, and you just need power electronics. But for a hybrid electric vehicle, ICE engines, all the mechanical engineers, they know ICE engines are very, very complicated as compared to a simple electric motor. So, but uh, a hybrid electric vehicle actually is a perfect candidate in a scenario where you want to manage that heat, you want to have a very good dynamic response, you want to drive your vehicle fast and all.
Thank you. Another question from Mr. Kaushik says, is it possible to increase the lifespan EV battery?
Lifespan can be increased by by your good practices of using the vehicle and good practices of charging the vehicle. If you charge your vehicle with a slow charger, then the battery life will be increased. Uh, if you do not put a lot of pressure on the battery in terms of accelerating and decelerating, then that also will increase the life of the battery. The dynamic response is the key, both in charging and discharging.
Okay, thank you, sir. Another question from Mr. Dr. Nagesh. Nagesh D is asking, what about the gradient resistance for the EVs? What about the gradient resistance for EVs?
Gradient resistance in terms of talking about the mechanical design.
Not sure, so he did not mention anything specific there.
Okay.
He can post the question on the feedback link. He can.
Okay, but based on what I understand, whenever you're designing a vehicle and you take gradient into account, the gravity part becomes very important, and the dead weight of the battery actually they add to the resistance that the vehicle has to face. So that is exactly why Tesla is using induction motor drives. Because in hills and all, when the dynamic response is becomes very important in those points, this induction motor, the performance of the induction motor combined with the battery and inverter, it becomes very handy at that point. So many models of Tesla, yeah, they are using induction motor. So gradient resistance, that is a challenge actually if you're talking in terms of the mechanical performance of the battery. So that can be overcome with the help of uh, the properly rated batteries and motor which can handle that amount of power. So in those cases, induction motor is a very good candidate.
Okay, sir. Thank you, sir. I think that's all we have from the questions from the participants in the chat box. Over to you, sir.
Thank you very much, Dr. Krishna Kumar sir, for sparing your valuable time to enrich the participants' knowledge related to the power technologies. And we got good information related to the queries also. Thank you very much, sir. Hope we'll have fruitful interactions in future also. Thank you once again. Dear participants, please respond to the feedback. Link is posted in the chat box. Please respond with your participant ID. With this one, we are closing today's section. Tomorrow again we will meet at 10 a.m. in the morning. Thank you, sir. Dr. Krishna Kumar, sir.
Sir, thank you very much, sir. Thank you to all the participants too.
Thank you, sir. Dear participants, if you haven't received your participant ID, please kindly contact Dr. Sridhar sir for the participant ID. For all the others, the participant ID has already been sent to your email IDs, your registered email IDs. So kindly fill the feedback form.
Sir, feedback